Bismillahirrahmanirrahim. Assalamu alaikum. I'm Dr. Sara Qureshi, CEO and co-founder of Aero Engine Craft Private Limited. Aero Engine Craft is a commercial aerospace R&D company working on environment-friendly aircraft engines. In addition, I'm a visiting academic at Cranfield University, UK, where I am part of a research group at the Propulsion Center headed by Professor Pericles Philidis. This group is working on contrail mitigation. I have a PhD in aerospace propulsion and a master's in aerospace dynamics, both from Cranfield University. The aviation industry is now pursuing environment-friendly technologies very aggressively post-pandemic, and we are trying to achieve this through the design and optimization for green engines, green aircraft, green rotorcraft, as well as green operations. And of course, the purpose is to reduce global warming, either by reducing fuel consumption in the aircraft or by mitigating noise pollution while we are looking at both carbon emissions and non-carbon emissions. Carbon emissions mostly comprise of carbon dioxide, and carbon dioxide is a phenomenon which is common to both the ground and the air, and it has a very wide spectrum of industrial contributors. So there is a fairly good understanding of carbon dioxide and its contribution, as well as methods to mitigate it and to reduce carbon emissions both on ground as well as in the air. A lot of solutions have been developed for ground-based industries to reduce carbon dioxide and are now being in some way transposed in the air to reduce carbon emissions. The combustion byproducts of any hydrocarbon fuel burn are water vapor and carbon dioxide, and water vapor is therefore one of the abundant non-carbon emission. Since water vapor has a variable residence time and lower residence time as compared to carbon dioxide, on the ground it is recycled quickly and does not contribute to global warming. However, at higher altitudes, this water vapor acts as a greenhouse gas and has a major role in contribution to global warming, and in that context, we can say that global warming contribution of water vapor is a phenomenon which is specific to the aviation industry, and therefore the understanding on it is limited, and that is my very purpose of setting up this presentation, to give you a brief understanding of the characteristics and behavior of water vapor in the atmosphere when it is released from the exhaust of an aircraft engine as an emission during flight, and its contribution to the greenhouse effect and hence to global warming. I have approached the subject through topics like water physics and thermochemistry that has led to the understanding of the manifestation of water vapor in the form of contrails as well as water vapor in the form of a greenhouse gas. We shall discuss contrails first and then focus on its behavior according to water physics. Water vapor emissions of aircraft engines exhaust as a global warming contributor. As you can see in this figure, there are three engines giving out a white smoke, which happens when water vapor is manifesting itself as a contrail. The fourth engine is a different engine or has some contrail suppression mechanism added to it, such that it gives out a transparent exhaust in the atmosphere. So let's discuss contrails first and then move on to water vapors. We all know that the source of contrails is water vapor, which is released from the aircraft engine exhaust as a combustion byproduct, and since it enters a very cold atmosphere, it condenses into a cloud. Initially, it forms a contrail and then disperses into an artificially induced cirrus cloud that have an optical depth and therefore reflect different wavelengths of the spectrum, both as incoming and outgoing radiation. And since the constituent is water vapor, which is a greenhouse gas, so they contribute to global warming. The likelihood of the formation of the contrails is in the upper troposphere at high altitudes at cruise flight conditions, and in the coming slides we shall explain why. They affect the Earth's radiation budget as well as the infrared signature by reflecting the infrared back to Earth and reflecting UV and visible spectrum to space, and a lot of studies and peer-reviewed research suggests that the radiative forcing of contrails is at least 5 times more than that of carbon dioxide. Carbon dioxide contributes around 3 4% to aviation-induced global warming, whereas contrails contribute around 15 to 20% to aviation-induced global warming. You can see in the figure there are some contrails directly being released from the aircraft, and then we have these dispersed clouds in the atmosphere. Here we have an aircraft releasing contrails, 4 contrail streaks out of the 4 engines, I believe. Some data available in literature suggests that the amount of moisture released by the burning of jet fuel from research aircraft was 1.7 grams of water for every meter of flight path. And then we have the total water measured in a consistent contrail producing around 20,000 to 40,000 grams of water for every meter of contrail path. So in this way, they are also suggesting that an additional phenomenon takes place since the initial condensation contrail also allows the moisture in the atmosphere to collide with it and coalesce with it to form a much larger cloud. From engine performance simulations, we do know that the water vapor content of core of exhaust in an engine is around 2.25% by mass, and the emission index of water for kerosene fuel is 1.25, which means that for every kilogram of kerosene fuel burn, 1.25 kilogram of water vapor is released, and calculations by volume suggest that a near to equal volume of water vapor is displaced because water is heavier than fuel. We carried out some simulations on Trent 900 fitted on an A380 aircraft, which is like a baseline specification, and we determined that 1.0715 kilograms per second of fuel is consumed by a single standard 3-spool turbofan engine during cruise flight, which means that 1.34 kilograms of water is produced by a 3-spool high bypass turbofan engine during cruise flight. And this implies that for an average 8-hour transatlantic flight, we would be making 160,000 kilograms of water with 4 engines on board. Here is some data on contrail cover by the Intergovernment Panel on Climate Change. A study was carried out that confirms that contrails cover about 0.2% of the Earth's surface at present, and it is likely to rise to 0.5% by 2050. And in the two figures you can see how the contrail cover has grown over the years, and so has its intensity. I would now like to briefly talk about clouds so that we understand the contrail phenomena better as well as the characteristics of water vapor. There are 4 major types of clouds: cirrus clouds, cumulus clouds, stratus clouds, and nimbus clouds. And as you can see in this picture, the one on the right is cirrus clouds, and their naturally occurring altitude is 6,000 to 12,000 meters, and they are made up of ice crystals and do not precipitate as rainfall. And such clouds occur at cruise flight altitude. Then we have cumulus clouds, which start from the altitude of 200 to 2,000 meters, and if they are moisture laden, they precipitate as rainfall. Then stratus clouds with an altitude of 500 to 3,000 meters, and they do cause rain and snow. And then we have the nimbus clouds, which are also low-lying clouds from 2,000 to 4,000 meters, and they contain a lot of moisture. They can cause thunderstorm and lightning with heavy rain. It seems that the characteristics of clouds and their capability to generate rainfall is a function of the altitude as well. Just to give you a reference, all these rain-causing clouds are below 2,000 meters, so all your weather cycle operates here. And then this is Mount Everest, and then we are flying, which is above 8,000 meters, and we are flying around 10,000 meters. So we just need to understand that if there is any moisture released from the aircraft at this altitude, there is no way that it would directly convert to rainfall, unless in some way that it sinks down to lower altitude. Again, this is reference to the different layers of the atmosphere and the cruise altitude. We are basically in the tropospherical region for subsonic commercial flying. In fact, at the boundary of the troposphere and stratosphere, which is called the UTLS, upper troposphere, lower stratosphere region, and in this region just above the troposphere up till 11,000 meters, and where cruise flight is generally a little above 10,000 meters for long-haul flights. Above the troposphere is the tropopause, where the temperature remains constant but the pressure changes, and then we have the stratosphere, and just below it we have the ozone layer. So we are close to the ozone layer but not exactly in that region. And this is how the temperature is also varying as the altitude varies. Now we will talk about the water physics, and this is basically the properties of water vapor, and here are different parameters and respective symbols and units and values for a few constant for the slides that follow. The characteristics of a water droplet are dependent on its particle size or its radius, so that can be determined by the Kelvin equation, which is a function of the surface tension, ambient pressure, and saturated vapor pressure. And then we have the formula to calculate the saturated vapor pressure, which is the function of your temperature. The latent heat of water vapor is also a function of the condensation temperature as well as the temperature. So now we just have to calculate the pressure and the temperature at different altitudes, and we have formulas for that. Your ambient pressure and temperature varies with h, which is the altitude, and the one for below 11,000 meters, which is your troposphere, and then we have a formula between 11,000 and 25,000 meters, which is your tropopause, and above 25,000 meters, which is your stratosphere. This is how your temperature varies, but in the context of subsonic flying, we are just looking at the troposphere at the moment. Then we have another approximation to calculate the saturated vapor pressure of water, which is through Taylor series. There are two methods. You can use the logarithmic equation or you can use the Taylor series expansion. Just giving you an idea of molecular size, we are dealing with water, carbon, nitrogen, carbon dioxide, and of course the kerosene fuel. Among the gases, we see that carbon dioxide is the heaviest, and in the exhaust we have nitrogen and water, which is the lightest molecule. This is the phase diagram of water, which shows a graph between temperature and pressure. Here you can see normal boiling point at 100 degrees Celsius at 1 atmosphere pressure. There is a triple point which lies on 0.01 degrees Celsius and 0.006 atmosphere. You can also see a critical point at the top of the graph, which is at a pressure of 217 atmosphere and a temperature of 373.99 degrees Celsius. Above this point, no temperature or pressure can condense water vapor. So in order to achieve condensation, the temperature and pressure should be equal or lower than this value. So now the natural phenomena of cloud formation and then the contrail formation is dependent on a number of factors, and of course we can determine the size of the condensate particle through the Kelvin equation. The Kelvin equation is a function of ambient pressure, saturated vapor pressure, and ambient temperature. If we look at the size of the condensate particle, we will notice that the size of water vapor formed within the engine has a negative radius, which means that it is an unstable particle which theoretically just evaporates at the moment it condenses, so it evaporates into a gaseous form. Generally, we are observing atmospheric conditions at cruise altitude, and we have naturally occurring clouds in the order of 0.1 microns. Since we have an average molecular diameter, we know that for the formation of clouds, a number of particles are needed. The phenomena for natural cloud formation is called collision coalescence, in which particles collide, condense, and other particles also condense on a single nucleus. So generally, the particle size is of almost 0.1 micron, and this is a cloud condensation nucleus, and it can coalesce with other particles to form clouds. In the case of 10 microns, direct clouds are formed. If the water vapor particle is in the order of 100 microns, then it is a proper water droplet. So this is the way we can determine the basic characteristics of water vapor at any given condition. You can find out the particle size and then you can determine whether it would be a cloud condensation nucleus, a water vapor, or a water droplet. There is also a graphical criterion determining the formation of contrails, and this is known as the Appelman criterion for contrail detection. I'm not going into this since its details are available in literature and the subject is very vast. So these are some calculations based on the temperatures and pressures that we simulated, and we noticed that the particle size is always negative, which implied that condensation is not taking place. And it is because it is a very unstable particle in a very hot atmosphere because the temperatures are high inside the engine. In the case of a bypass nozzle, the particle size is 1 micron and it is in the order of a naturally occurring cloud. The next table shows how the temperature and pressure varies with altitude. As you increase the altitude, the temperature is reducing and the pressure is reducing. And therefore, the saturated vapor pressure is also reducing. So, in its effect, condensation is taking place in the order that it appears as a naturally occurring cloud. In this calculation, we calculated the pressure required at a given temperature to condense water. What we did was that we fixed the particle size to 1000 microns to convert it into a raindrop, and then we figured out the pressure required to condense it. So this is the way we can work out the different ways to find the properties existing in a particular form, such as the vapor, the contrail, or the cloud condensation nucleus, or a condensed droplet. This also explains why lower altitudes and temperatures are more conducive to rainfall precipitation. Contrail prevention has two basic concepts. You can either disperse the contrail into a vapor that you make the particle size smaller, and the main concept is that you turn it so small that it can form a cloud condensation nucleus but cannot form a visible contrail. Or you can increase the size of the water particle through coalescence and hence nucleate the contrail into water. Our objective is contrail prevention. There are two methods. For preventing nucleation, people use chemical seeding where they seed it into ice crystals or they disperse it by adding more energy to it through ultrasound or microwave. Or we optimize the trajectory path of flight in the sense that we fly higher or lower or in a region where contrails cannot be formed. For creating nucleation to eliminate contrails and to condense it into a water droplet, you can go for either conventional heat exchange mechanism for water recovery, which is temperature based, or through pressure based condensation. Here again you can see the different methods which can be used to prevent contrail formation. There is a lot of research available on the subject where people have evaluated the application of these techniques to avoid contrails. But so far all these areas are in the research phase, and it hasn't really gone into the people haven't really looked into the commercial aspect of the different technologies available. The aspect of thermochemistry of the water vapor produced inside the engine has also been covered. A quantitative study has been carried out for the energy absorption regimes of combustion gases. This research was based on some prior data available on an extensive study carried out on carbon dioxide and nitrogen systems for exhaust plumes of jet engine and CO2N2 laser systems, as well as for the Mars atmosphere, where carbon dioxide and nitrogen are the main constituents of its atmosphere. There is evidence for intermolecular and intramolecular energy transitions between the combustion gases. The different molecules exchange energy among themselves in the three modes of energy: the translational energy, which is the kinetic energy or speed of the gas, the rotational energy, which is the function of heat, and the vibrational energy, which causes photonic excitation. Water vapor and carbon dioxide both absorb and emit in the infrared spectrum in the vibrational mode of energy, and therefore contribute to the greenhouse effect. In the case of water being condensed out, these transitions allow carbon dioxide and nitrogen to act as a heat sink for the latent heat of water vapor. A detailed report shall be published on the thermochemistry of the combustion, since it is a very vast topic and cannot be covered in this presentation. So here are some references on the various topics that we have covered. Contrails, atmospheric physics, Contrail. I would like to acknowledge Cranfield University. A lot of this data that has been compiled was researched and processed during the course of my PhD at the Propulsion Center, School of Aerospace, under the supervision of Professor Pilidis and also with the co-supervision of Professor Singh. Professor Singh laid the foundation of the Contrail mitigation group at the Propulsion Center at Cranfield University. A considerable amount of research has been done on it over the years as master's and PhD thesis. And I would also like to acknowledge some colleagues at Aero Engine Craft, Mr. Masood Latif Qureshi, who is the inventor for the technology that we are working on for contrail mitigation. And some research has been done on the thermochemistry of combustion in collaboration with Dr. Romana Qureshi from Quaid-e-Azam University. Thank you very much for listening. I hope that this presentation broadens your understanding of the environmental impact of water vapor when it is released by jet engines as a combustion byproduct during flight. The purpose of this presentation was to determine the impact of this fairly occurring non-carbon emission so that we can target the right technology to mitigate it and also enable funding bodies to prioritize accordingly. Here are some links to my work just in case somebody is interested. Thank you very much. Allah Hafiz.